Rushed or even envelopes given to the array of envelopes denote width, height. One envelope can be fit into another if and only if both the width and the height of one is greater than the one. Both will need to be larger. We can fit into another one. Return the max number of envelopes you can rush a door. Put one inside the other. We are given like this one. So the max number of envelopes you can do is 3. 2, 3, going to 5, 4, then going to 6, 7. In this case, there's only one can do. So this problem, because we are looking for the maximum number of the envelope you can do, is similar to the LIS longest increasing subsequence. First, we can sort by the height, and if there is a tie, we need to increasing sort by the height, by the width increasing. Make sure each width is increasing ordered, and we can, if there's a tie, we need to sort by height decreasing, because if we our goal is to run the longest increasing subsequence on the height, because our width is already ordered. In case there's a tie in the width, we don't want to encounter, like this example, we don't want to have the 4 and the 7 in the longest sequence, so we need to prevent that case. We prevent the case, we sort if there's a tie in the width, we sort the height in decreasing order, and finally we run the LIS only on the one-dimensional array about the height. That way we can get the final result. So let's do it. So first we need to sort this array, sort this envelopes. We are given 2. If the first one is equal to the second one, if they are equal, we are needed to decrease, which means we will using the next one minus the first one. If they are not equal, we are increasing order. We are using the increasing order. Okay, so now we have heights. For we are interested in the second one, which is the height. After that, we run the longest increasing subsequence on this one-dimensional height array. So now we'll try to find the longest increasing subsequence. Idea is to build the DP array. And and for smallest one is 1. It's itself it's LIS. Now we are looking for from the first one to the next one. We needed to check, look back. If the previous one is smaller than the current one, then we can update our current position. And we need 1 plus the previous LIS. The final result will be the largest one in the DP. To return the result. Okay, let's run this algorithm and make sure it works. Wow, why it's time exceeded. Let's analyze the time complexity here. So if we use this way to solve it, now here we are using n log n to sort the input array. We get the height. Here we will input this array to here is when the O of n here will be n square, and here will be n log n, and here the n is the square. So there 2 will be denoted to the previous one. Final time complexity will be n squared log n. I know here is something we can optimize to n log n using binary search. But it's not the bottleneck. Bottleneck is the sort part. How can we improve from here? This is the algorithm first one. We do the sort. Space complexity will be O(n). And calculate the length of input. Both sort array and find the implementation is n log n. So we need to improve here, not use the old n squared algorithm. We need to using the n log n here, and because we are not exactly needed to know the final order about the output, we only care about the length. So in that way, let me check here. Binary search DP. idea is to each one we find let's give an example here. So if it's like this way, we always start with, so in this example the final result will be 3, right? So we go through, we have a list, or we add this is our final result, and we are going to loop for each I. Okay, if so current number is list is not empty, and the pick last pick the last is smaller than the current one. There's we will add the last the current one into this one. If not, if not, we will find the position. We will find binary search. The position is the current one. The current position is okay. Current position here. The way is to find the J such that J smaller than I, and the J is the first larger. I need to replace the one J. Let's find the index J such that is the first one larger than the current one, and I need to replace the current one to the J position. Replace the current one. Replace or swap. Replace J with the current values. Finally, we'll just return the list of the size. Index looking for the previous one. J is 0 from the beginning, while J is small. Array J is smaller, too small. I want a large one, small, so it will never be the case. Compare the middle. The middle is too small, and to the left, to the middle, else too small, it cannot be the case. If maybe the case here, so it's less than middle, say the middle. So here, now my list for this example, my list here will be first is 1, and it's still bigger than the last one, so it's still 5, and here it's 3. 3 is not larger than 5, so I need to find the previous one to replace. Ideally, I will replace this one. List. Oh, I can directly put the list, not the array, right? I can put the list here and just give the current number, and it will give me the thing. Left, right, while left, middle if the smaller than current. Will never be the case, so the left part will go to this one, else the right one may be the case, and eventually we need to return the m. Return to the right if they're the same. Replace so it's list the set the position with the current one. Index is -1. position. So in this case, they don't search the right one. List only if it's empty. In this case, if it's empty, or if it's empty, we can directly add the last one. If not empty and the last one is smaller, we can also append to the list. Okay, now we can finally get the things go through. We optimize from the ON square to the ON log n using the binary search here, and the total time capacity will be n log n. That's the case here.